Hello again. Fancy meeting you here. I suspect you came just from the chapter 1 video. We are going to be diving in here to chapter 2, which is all about abstraction, refinement, and encapsulation. Pop quiz before we go through any of the rest of the slides. Take a moment to think. From the chapter readings, could you define what abstraction is, what refinement is, and what encapsulation is? These are great exam questions, so I highly recommend you being able to just kind of pull that information up in your brain. And if you're not there yet, that's okay. You'll just want to make sure that you keep reminding yourself what those terms mean throughout the course so that when it does come to final exam time, those definitions are already there. I'm going to go through what they mean right now as well, so if you want a refresher, stay tuned. Abstraction, refinement, and encapsulation. We talked about them in the chapter and gave examples of where you would see these things kind of in our day-to-day lives. They are fundamental processes for all things to do with programming and computer science. It's a very, very common way that we think about programming and we think about developing code. And it's exactly what we'll use to start breaking down problems into smaller pieces, as well as thinking about them at kind of like a high level and how we can approach them. So you'll get very used to using these different kinds of terms and actually practicing them as you go and design your own programs starting in the next chapter. So abstraction is going to be a strategic removal of detail from the algorithm. So you can think of it like a map. A map isn't going to contain every single tree and blade of grass and whatever else detail you could see by just looking out your window. It's going to only include the detail that's important to the viewer of that. So if we were to go onto Google right now and you put in your address, the detail that you would see would be like the streets around it. Maybe it has some outlines of some houses. If you go into Street View, you can kind of see the different things that are around. But when you're just looking at that overview of the map, it's not even going to say there's a power pole here or a fire hydrant over here, various things like that. There's strategic details that have been removed from that map to serve the purpose. Because the purpose of something like a Google Maps is really to show you the different streets, to help you plan from how you get to A to B, things like that. If you were an electrician like my husband is, when he looks at house plans, the house plans that he sees have different details in them and other details that are removed because the electrical details are the most important to him. Whereas the plumber might have house plans that focus more on the plumbing details and have abstracted out those electrical details, right? So abstraction, you're thinking about the audience that is seeing this, and you're saying what details are important for that audience to see and what details are not important for that audience to see. Refinement is when we would add more details into an algorithm. So I'm not sure if any of you have seen, I guess this is probably absolutely is dating me, but it was on YouTube and TikTok and probably Instagram Reels, probably where I saw it because I'm a millennial, where there was a parent and they had a child and they were saying, okay, tell me how to make a peanut butter and jelly sandwich. And it was all the funny different ways of them just taking those instructions from that child and following them to the T. So, okay, grab the peanut butter and put it on the bread. And you just take the jar of the peanut butter and put it right on the bread. And the kid would laugh and realize, oh, hey, I actually need to refine that step a little bit more and unscrew the lid of the peanut butter and scoop it out. And oh wait, actually first pick up a knife and then scoop out the peanut butter with a knife and spread it on the bread. And of course, the child didn't know they were doing refinement, but truly that's what they're doing in those videos. And you can Google it and look it up. I'll see if I can find a link and I'll post it in the course. It's quite funny. At least I found it quite funny. But that process of saying, okay, adding more details in, giving the person more instructions on how to do the task or the computer or the whatever it is would be a process of refinement. And we use that quite often in computer science where we'll say, here are the high level steps. Now let's drill down in that step and add in all of those details once we've kind of figured out the overall flow of how we want things to work. We only have 2 short exercises in this chapter, so I'm going to zoom through one, like part A of both of those, and you can do part B on your own. We have 2 different algorithms here, both for making a snowman, and we want to know which one's more abstract. I'll give you a hint. If abstraction is removing detail, and one of our algorithms is 3 lines shorter than the other one, and we want to know which one's more abstract, do we think it's the one with more lines? Probably not. Probably not. Typically, a more abstract algorithm is going to be the more concise algorithm, so the shorter algorithm. And in this case, that would be the first one that only has really 3 main tasks associated with it. When we look at the one below, it's giving a lot more detail. There's detail about how large the different balls of snow need to be and the order in which we need to place them onto each other. Lots of detail, good detail for certain audiences, but if we wanted it to be abstract, for sure the top algorithm here is the one that is more abstract. We just need 3 balls of snow, we stack them on top of each other, and then we put some sticks in for arms. Great. I'll let you do the same type of exercise here with this second example. I wonder which one it will be that is more abstract. All right, encapsulation is the third process that we talked about, and it is just a principle where we would take related actions and group them together and give them a name. Later on, we'll be calling these things functions. So where we say all of these related tasks for the computer should be grouped together, given a name. And the reason we give them a name is so that we can call it multiple times, right? And so we don't have to say, oh, go do all of these things again and la 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 la. We can just say, go do this, go do this. And then the computer can go in and look and say, okay, this means X, Y, and Z task, right? We do the same things when we're giving instructions to humans all of the time, where we encapsulate or group common tasks together that are related to like a common goal you could think of. So we'll go through one example here, and then there'll be a different example later on. So we have this algorithm. It says it's called call emergency number. Okay, good one. And we have a series of tasks associated with that. So find the nearest phone, pick up the phone receiver, dial 9, dial 1, and then wait for an emergency operator to pick up. And our task is to perform at least one encapsulation with this. And so similarly to last chapter, your solutions to these things might be very different than the solution I present or the solution that's in the actual solution document, but it might still be a perfectly valid and correct solution. There's lots of different ways you can interpret this, and just because yours doesn't necessarily identically match mine does not mean it's wrong. And if you would like to know if your approach was correct, post it on the discussion boards, right? So when I'm looking at this, I'm trying to see, okay, if I need to perform an encapsulation, where are tasks that are similar on here, that are achieving a similar goal? So there's maybe some tasks about picking up a phone or finding the phone. There's definitely tasks about dialing a number. And then there's the one remaining task for waiting for an emergency operator to pick up. So when I'm looking at this, I'm like, okay, I think where I would like to start is this part here. These 3, oops. Oh my goodness, just adding so many extra things here. These 3 tasks on lines 5, 6, and 8 that are all related to dialing that number, that 911. I'm going to encapsulate those because they're all working towards achieving this common sub-goal of dialing the number. So instead of having all of those together, what I would do is replace that line 5, 6, and 7 with a new thing called dial 911. And you'll notice I didn't add a space because computer scientists hate spaces, but we'll get on to that later. But that would be what I would call my new algorithm. That would then have those 3 lines as tasks in that algorithm. And so I'm encapsulating them into a larger, or into a sub-algorithm called dial 911. And so my final algorithm here would just be find nearest phone, pick up receiver, dial 911, wait for emergency operator to pick up. And these details would be encapsulated into this larger dial 911. All right? Here's another exercise for you to work on where we were asking for you to perform at least 2 encapsulations. So take a look at this algorithm. Try to identify, okay, what tasks are kind of related to some sub-goals here that we could encapsulate into other algorithms and then replace. And see what you can come up with. Again, post on the discussion if you have any questions or finding things tricky or want us to check answers. And as always, check the solutions. Once you're done that, make sure you attempt lab 1 and 2 since you'll be ready for that now. Remember with the labs, you can repeat or submit answers as many times as you want with no penalty. So you can continue to submit the answers until you get the correct answer, and you should be able to get 100% on that, right? I have faith in you. Have fun, and we'll see you in chapter 3, where we're going to start working with programming in processing.